Example 24. The granular material exerts the distributed loading on the beam as shown in the figure. Determine the magnitude and location of the equivalent resultant of this load. So we have a uh, if we can break this, what we can do in here is that we will do some manipulation. How so? If you can observe that at point B, we have 50-pound foot load, yeah, measure of our load, and at point A, we have 100 pound per foot, yeah. So just like what we did sa example 23, we'll have I will present two options of the solution. Okay, so we have, let us say, solution one. Solution one. So if we rewrite this one, redraw rather, so we have over the length A, B, we have yun, this one. And it's going, okay, distributed loading. Okay, so if what we had so far was triangular, right? And we can say that if only our complicated distributed loading can be expressed as if rectangular loading and triangular loading, mas mapadali unta. But if you can observe, this is 100, right? 150. So this is 100 here, 100, and this is 50 pound per foot. Anyway, so we will break this loading into two. How so? We will break it as one rectangular loading and one triangular loading. So we'll have this one. You have two. Okay. So for our rectangular, its height, maximum height, would be our 50 pound per feet, right? And we know that this is 9 feet. Pound per foot. Pound per feet? Pound per foot. Yeah. And that's over 9 feet. For our triangular loading now, we know that the entire A is 100. So if we take 50 from it, so the remaining maximum height of our triangular loading will only be this one here, will now become 50 pound per foot, right? So if you guess it right, that we will have two forces now. We have the resultant force of our triangular loading and the resultant force of our rectangular loading. And only then, after we add up those two forces, we can calculate for the overall resultant of this uh, kind of loading. So we have, let us say, this is my F sub uh, F sub tri. Okay, for my triangular loading and my, let us call this as my F sub rect, right, for my rectangular loading. So since we are not provided with equations, we'll just use what we have learned in solution option B. for in our example 23, that our force, resultant force, is equal to the area of our loading, right? So we have F sub tri is equal to 1/2. Let me write it as area of my triangular loading. And the area of my triangular loading is 1/2 base times height. And my base is the length, which is 9 feet, times my height, maximum height would only now be 50 pounds. 50. So my resultant force of my triangular loading is equal to 50 times 9, 450 divided by 2 is 225 pounds. Now for my, uh, what do you call this? For my location of my resultant force, for my triangular loading is x, a bar x is equal to, so since if you can observe, we have a fixed at point A, right? And overhanging at point B. So we can say I want to measure it. Let us say I want to measure it from A. Okay, so if you want to measure it from A, that is the back of my triangle or the base of my triangle, right? So, and tip or back, yeah. So that means I'll be using 1/3 times 9. So my x prime, bar x is equal to 3 feet. Now this 3 feet is measured from A. Okay, now for my force rectangular is equal to area of my rectangle. And that is equal to base times height. And my base is 9. And my height this time is 50. So my force rectangular is equal to 450. 450 pounds. And my location, so of course, if we measure, if we cut our rectangle into two pieces, meaning kung asa yung centroid, nagod siya sa center sa tunga gyud, you can separate those two gyud, right, into equal sizes. So it means that our formula for the location or the centroid of our rectangle is 1/2 times entire length, and that is 9. So bar x is equal to 4.5 feet measured from A or B. Okay, now so of course we will calculate now for the resultant. So for our resultant, F sub R is equal to the sum of all forces in the Y. Now, like I said, I don't have to assume now the direction because by inspection, we can say na wala na gyud lain pang force nag-act in our body, only going down nga force. So, we can assume na going down good ang atong resultant force. So, this is our force of our triangular loading plus the force of our rectangular loading. And that is equal to 225 to 5 plus 450 pounds. So our resultant is equal to 225 plus 450. That's 675 pounds. So this is the magnitude of our resultant force. Now, so if we try to redraw our structure, so that's A, B, and we know that this entire length is 9 feet, and Let us say this is my resultant force, F sub R. What is this length? Right. So we know that uh, in order for us to know this distance, we will be using the knowledge we got in finding the moment of our moment of a force. Okay, so moment, resultant moment about A is equal to all the moment that acts about point A, assuming counterclockwise positive. Right? Okay. So for our resultant moments, of course, we have F sub R. Now, we are taking moment about point A here. Now, question. Uh, I know you will not answer it, but just an analysis. F sub R causes a clockwise moment about point A. And since we are assuming that counterclockwise moments are positive, so it means F sub R here, for this case, becomes negative. So that is negative F sub R times its perpendicular distance, which is x, is equal to, then we go back here. For our F try, let's just copy it. And again, F try and resultant force of our triangular loading and the resultant force of our rectangular loading all create a clockwise moment about point A. So therefore, both of these forces will be negative. So that's negative F try times X bar try minus F rectangular loading times bar X rectangular loading. So we substitute all of the values. But before that, what we can do also is we can simplify this without substituting yet the values. That is, we divide both sides by negative F sub R because we have calculated our F sub R already. F sub R. So that's X is equal to negative F try bar X try minus F rectangular bar X rectangular divided by negative F sub R. Then we substitute, and of course, since we have a negative numerator and a negative denominator, so both our final answer will be positive. So what we can do is that this is equal to F try is mm, 225. So that's positive 225 times the perpendicular distance of F try from A, that is 3 feet. So that's 3 plus F react, that's not react, but F rect is 450 times the perpendicular distance, which is 4.5. So times 4.5, all of this expression is divided by 675. So therefore, our location of the resultant force, they should be bar x, or just x, because they are not the centroid rather. So that's 225 times 3 plus 450 times 4.5 divided by 675, and that is 4 feet from A. So if we substitute if we input our resultant force in our original diagram, so this is, we know this is 3, this is 4.5, so maybe around here, this is our F sub R. So another option on how we're going to find for the resultant and its location is simply we write, let us say, solution B. 2. Okay. So if this is our A and this is B, we have 100 to 500. No, 50. Sorry, we found you can, then this is 100 pound per feet. So what we can do is we can also, instead of having a triangle and a rectangle, we can also have triangle, triangle. So meaning we will cut it this way. So we have a triangular loading that looks like this one, like a full triangle, and this triangle, small triangle at the bottom. Okay, so since we both have, they are both triangles, sorry. So let's just have this one, let us say this one as, for my bigger triangle as f sub 1, and the resultant of my smaller triangle to be f sub 2. Okay, so what we're going to do is, for our f sub 1, since that is still equal to the area of our triangle, right? But of course, that is 1/2 base times height. So the only difference is that instead of having uh 50 as our height, we will be using 100. So f sub 1 is equal to 9 times 100 times 0.5 or 1/2. And f sub 1 is 450. Now, of course, why 100? Because again, we did not cut the bottom of our bigger triangle, right? So we use the entire 100 pound-feet as our height for the bigger triangle. So of course, again, the same case, it's bar x bar x sub 1 is, if we measure it from A, still 1/3, because again, that is the bottom of our bigger triangle, or the base of our bigger triangle. So that is 1/3 times 9. So x bar 1 is equal to 3 feet from A. So for our bigger triangle, so we have f sub 2. F sub 2 is still 1/2 base times height, and our base is still 9, and our height is 50. So this becomes f sub 2 is equal to 90 times 50, 9 times 50 divided by 2, that's 225. This is pounds, this is still pounds, and our bar x2. So take note, if we want to measure it from A, that is now the tip of our smaller triangle. So this becomes now 2 over 3 times 9. So that's bar x sub 2 is equal to 6 feet from A. Okay, so if we do moment summation, of course, we will still end up with this formula. So let's just copy it this here. Of course, our resultant is F sub R is equal to 225 plus 450 is still 675. Ito our resultant force. And for our x, this is still equal to f sub 1 times bar x1 plus f sub 2 bar x2 divided by our resultant, right? But for our f sub 1, that is our bigger triangle, that's 450 and its perpendicular distance from A is 3 plus f sub 2 is 225 and the perpendicular distance of 2 to 5 is 6 from A divided by 675. So our X, which is the location of our resultant force from A, 450 times 3 plus 225 times 6 divided by 675 is still 4 feet from A. Okay, so we have two options as to how we're going to solve this kind of problems.